When we were looking at the reduced row echelon form of an augmented matrix, we noticed that the exact location of the leading ones actually had a big influence in what the collection of solutions looked like. And the reason for that was, remember, wherever you have a leading one, if it's something like this, so this is the X column, this is the Y column, this is the Z column. In reduced row echelon form, wherever you have a leading one, that position, that variable, is going to end up being determined by the system of equations. And wherever you don't have a leading one, like for this Y column, you're going to get a free parameter that can be anything. So here t can be anything. So the location of these leading ones is actually very important for what the solution set is going to look like. So for that reason, we give a special name to the positions that have these leading ones. So a pivot position in a matrix is just a position in the matrix that has a leading one in its reduced row echelon form, or in its row reduced form. So in this sketch that in this partially written down matrix, this one here is a pivot position because this, at least if everything else is 0 down here, then this matrix is in row reduced form, or row echelon form. So this is a pivot position. This one here is also a pivot position, but this too isn't a pivot position. And then a pivot column is in one of these row echelon form matrices is just a column that contains a pivot position. So this first column is a pivot column, this third column is a pivot column, but the second column isn't. So, columns that correspond to pivot columns give us variables that are determined or locked down by the corresponding system of equations, and columns that are not pivot columns correspond to variables that are free parameters. All right, just to make sure we understand how this works, let's find the pivot positions and columns for this matrix. So to figure out the pivot positions and the pivot columns, we have to have it in row echelon form, or reduced row echelon form even. So we'll need to reduce this matrix. So let's do some row operations. So we need to use this 1 in the upper left-hand corner to eliminate the stuff below it. So row 2, we need to subtract 2 times row 1, and that'll zero out that 2 there. And then for row 3, we need to add row 1. And then, so first row isn't going to change, so 1, 3, 1, 4. For the second row, so row 2 minus 2 times row 1, so 2 minus 2 is 0, 6 minus 6 is 0, and then 2 minus 2 also 0, so nothing but zeros here. And then 8 minus 2 times 4 also 0, so nothing but zeros for that whole row. And then now we take third row and add the first row, so 0, 0, 1, 6. Okay. Now from here we could, we don't quite have it in row echelon form because, right, remember any rows that are 0 have to be moved to the bottom. So now we just have to interchange row 2 and row 3. So we get 1, 3, 1, 4, 0, 0, 1, 6, 0, 0, 0, 0. Okay. So now the pivot positions are just the leading ones. So there's a leading one, that's a pivot position, and here's a leading one, that's a pivot position. And so the columns that are pivot columns are the first column and the third column. All right, so let's see how we can put this all together to solve a system of linear equations. So here's a system. To solve this system, the first thing we're going to have to do is write down its augmented matrix. So let's see, 2, minus 2, 8, and 12. And then for the second row, minus 1, 3, minus 2, and minus 6. So here's our augmented matrix. Now we just need to do row operations to get this into row echelon form, or maybe reduced row echelon form. Usually, if I'm going to need free parameters, then I go all the way to reduced row echelon form. So for our first operation, let's see, we want a leading 1 in this first row, so let's divide the first row by 2. So that gives us 1, minus 1, 4, 6. And then second row isn't changing, so minus 1, 3, minus 2, minus 6. All right, now we need to take the second row and add the first row to it, just to zero out this minus 1 right here. So this gives us 1, minus 1, 4, 6, and then 0, 2, 2, 0. And let's see, now we need to make this leading entry, this leading 2, we need that to be a 1. So we need to take the second row and divide it by 2. This doesn't change the first row. First row is still 1, minus 1, 4, 6. And so second row is 0, 1, 1, 0. Now, because we have one of our variable columns here, it doesn't have a leading 1, we know we're going to get infinitely many solutions, right? Because this is not, because there's a column other than our augmented column, because there's a column that is not a pivot column, we're going to need a parameter, which means there will be infinitely many solutions. And in this case, I like to go all the way to reduced row echelon form. So to do that, we need to use this leading 1 to get rid of that minus 1 that's above it. So we need to take row 1 and add row 2. Okay, so this is going to give us 1, 0, 5, 6, and 0, 1, 1, 0. Okay, so here's our resulting matrix. This is in reduced row echelon form. So the non-pivot column, there's a non-pivot column which is right here, right, other than the augmented column. Right? The non-augmented, non-pivot column is this third column, which this third column represents the variable z. So z is going to be a free parameter. Z, so this can be anything. So we have a free parameter t. Y is determined by this second row. So y is 0 minus z. Remember, in our heads, we have to take this 1z and move it to the other side. So y is minus z. And then the first row tells us that x is 6. And then remember, we have to move this 5z to the other side. So 6 minus 5z, but z is really t. Oh, so this z here should be t as well. All right, so our solution is x is 6 minus 5t, y is minus t, z is t, and t is a free parameter that can be anything.